Hello, and today we're going to be talking about atomic spectra. This is kind of going off of our electron configuration. We're going to talk more about the nature of electrons when it comes to introducing energy to them, which produces atomic spectra. So we're going to dive into that just a little bit in regards to application of why we study electrons and how we use them in experimentation. So there's two primary electron states. There's the ground state. The ground state is the lowest energy electron position. It's the lazy electron position. It's the normal position of electrons. It's also referred to as the normal state of electrons. The excited state of electrons is a temporary, short-lived electron position of a higher energy state than its ground state. So it's when energy is introduced to an electron and it jumps into a higher energy state or a higher principal quantum number to produce any type of reactivity, reaction, so on and so forth. The electron can only stay in there for only a few nanoseconds at a time, though. So it grabs the energy and quickly gives it back just as quickly as it got it. So it's something that happens very, very quickly. Sorry about that. All right, so kind of jump into excited electron states. To excite an electron, the electron must be exposed to some type of energy from an outside source. When the electron absorbs the energy, the electron jumps from the normal orbit or orbital that it's in to a higher energy level orbit or orbital that it's not in. So most of the time, the outside energy that you may see electrons be exposed to are in the form of photons, which are little particles of light. So what will happen is that the photon will come in, it will hit the electron will absorb that energy from the photon, and then it will bounce up to another higher energy level. And however much energy is in that photon determines where exactly it ends up. It doesn't necessarily mean it's going to jump up one by one. It may jump up only one level, it may jump up 5 levels. It just depends on how high of energy that light hits the electron. So then what happens is that as soon as that excitation occurs, the electron wants to return back to its ground state. It's an excited state, an unstable state. And everything in Mother Nature wants to get back to as normal, as stable of a state as possible. So the electron wants to give back the energy as soon as possible. So what it does is it emits the same amount of energy that was given to it. That is equivalent to the energy level between the excited state that it's in and the ground state that it's in. So for example, this is a difference in energy. The space in between these two energy levels is a difference in energy. So for the electron to go from here to here, the energy difference has to be equivalent to the amount of energy the electron has to give off for it to be back down its original state. So it emits most of the time and also forms of light as well, which is how we see colors. And how atoms are arranged and how their electrons are excited and how they move between their states is what allows us to kind of see colors, how they absorb and reflect light. And so it will give it off, and that electron will jump back down to its original ground state, and that energy goes away. So atomic emission, all elements have a variety of electrons at a variety of energy levels, and we know that from the previous electron configurations videos that we've done. Due to this, each element is able to emit particular wavelengths of light after their electrons are excited. Because since each atom has a different number of electrons spread out in different ways, through different shaped orbitals and different energy levels, they're able to produce different lights that can be emitted off of them that we can see through the human eye. Each element's particular wavelength emission is based on the element's nuclear charge, which we'll kind of dive further into later on in the year. Some of the light that is emitted can be found within the visible spectrum of light. Visible meaning that we can see it with our eyes. There are types of spectrums that we cannot see. We actually have to use special equipment. For example, ultraviolet and infrared. Those and gamma rays and radio waves we can't see. We can feel them to an extent, or they can react with our body. But we visually cannot see them because the retinas and corneas of our eyes are not built to receive that information and interpret it to a way that we can actually see it. So the visible spectrum of light ranges between the wavelengths of light of 400 nanometers, so that's 400 times 10 to the negative 9th meters, and 750 nanometers, which is 750 times 10 to the negative 9th meters as well. So very, 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 very small wavelengths of light that we can see. And we see it through our color spectrum. So 750 nanometers on the left, which the longer the wavelength, the more red it gets, and then the 400 nanometers, the shorter the wavelength, the more purple it gets. The big thing with this too is that the red light is low energy, the purple light is higher energy, because the more scrunched up the wavelength is, the more energy can pass through it at one time. Besides the longer wavelengths, that can only so much energy can pass at a particular time. Another way you can always do this is you can always remember Roy G. Biv. So if you write this on a test, you can just write 750 ROYGBIV and then 400 nanometers. This might be something that you probably learned in your physics class too. So just a little refresher there. Atomic spectrum. So when the light produced by the electron passes through a prism, which if you've seen Dark Side of the Moon, you know, the album cover for Pink Floyd, white light passes through a prism like a triangle, and then all this light, multiple colored light comes out. That's exactly what happens. It passes through some type of prism where the light is spread out into different colors and different wavelengths that we can see or what we can't see. That emission spectrum is produced when it happens. So the fact that each element produces different wavelengths of light after excitation of its electrons, the unique atomic spectrums are present for each element. So each element has a unique atomic spectrum that is produced when the light of that element passes through a prism. The nice thing is that since all the elements have their unique spectrum, we can use these spectrums to identify elements just based off the light that they emit after excitation. This is the foundation of an analytical technique called spectroscopy. Spectral meaning light, scopy means the study using light, something like that. So this is a very, very common form of analysis that chemists and physicists use, especially when it comes to analyzing chemical substances. I've played around with spectrometers for many years of my life. It's pretty fun and sophisticated stuff. So if you ever want to talk more about it, please come talk to me. I'll dive a little bit deeper into what this is too, and maybe have a couple examples that we can do in class as well. But for example, let's look at hydrogen. If I was to give hydrogen energy to its electrons, and the electrons emitted light through a prism, the visible spectrum would show little thin lines like this. Okay. Now it has 5 distinct lines, 3 purple violetish, and then you have one that's kind of a light blue greenish color, and one that's in the red color. Those bands represent different widths of energy that the electron can travel. But you're probably asking yourself, well, Mr. Harville, there's only one electron in hydrogen. True. Very true. But the thing is that the electron can be in multiple places at once, and it can also be excited to levels that you may not fully understand, but it can produce these types of light. So hydrogen is defined by this particular emission spectrum. If I was to look at carbon, carbon has many more electrons in it, which means it can produce many more lines. So if you kind of counted them up, there's a couple of lines that are kind of similar. Like there's 2 lines here, looks like 2 lines here, maybe 2 lines here, but they spread from, you know, the violet side all the way to the red side. But this is unique to carbon. So if I have this and I was lining it up with something that I had from an instrument, I can, you know, deduct based off position of those lines in regards to wavelengths and say, oh, there's carbon in this compound. Neon also, with being a noble gas and a little bit higher than carbon in regards to electrons, produces plenty of other lights, which is the reason why what's really cool is that neon signs, they can all be made of different colors because neon can produce different colors. The way those colors are produced depends on the amount of energy those electrons are exposed to. So neon lights that have, you know, purple lights to them, they may be exposed to a way higher voltage than maybe neon lights that have red lights in them that requires less energy. So just be aware of that. I mean, neon's a very versatile gas that we use for practical applications like that. We also use neon a lot because, one, it's an inert gas. It doesn't want to react with anything. And we use it a lot in spectroscopy in regards to chambers and stuff that we need to fill with compounds and shoot light through and so on and so forth. So this is kind of just a general idea, a general animation of what spectroscopy does. So if I was to break down a spectrometer, this is atomic emission spectrometer. And what we do is that there's this flame here, and there's this sample that we would stick a tube in. That, let's say this was sodium chloride or something like that. I would stick sodium chloride. It would get sucked up into this tube, and then acetylene, which is fuel. Also, it's ethene too. Air, which is the oxidant, which allows it to combust, and a drain for any excess water and stuff like that from the combustion or condensed CO2. It'll get cut up, and then it will be shot and ignited into this flame. Well, this flame, what happens is that it'll produce a particular color. But to filtrate out the calcium or the sodium that's in there, since it's a particular color, I will shoot a light that's equivalent to a level of sodium electrons through this, and it will filter through this grating, and then it will spread out into light that can be analyzed into a computer, and it can tell me the concentration of sodium within that sodium chloride solution. I know it doesn't really make too much sense maybe, but that's kind of the generic idea of how spectroscopy works. And this is just atomic emission spectroscopy, and then it turns into absorption. That's with the light. So a very similar setup. It just depends on what type of experiment that you're needing to do. But this is a generic setup for spectroscopy. All right, so that's the end of this video. If you have any questions in regards to spectroscopy or atomic spectra or spectrums, please come talk to me, email me. I'll try to do what I can in class to kind of further along this subject. But, if you do continue on your scientific career, you're most definitely going to be playing with spectrometers. So, if for some reason you need to dive into more how spectrometers work, I have texts and stuff that you can look into. I've got textbooks. I've got articles that you can look into. So again, if you have any questions, come talk to me. Otherwise, thanks for watching this video, and I hope to see you in class and in the next one. Bye.